Hello guys, how are you? Hope you had a good day today. Okay, so I'll be doing a short video on the um, one of the functions of ECE51 microcontroller, which is the PSW, as the programmable program status word, just like I mentioned the last time that I'm going to do. And before I go into that, um, the last exercise we were working on, which is the 7 segment display. Um, we're trying to switch between the segments of the multiplexed 7 segment display, and we actually ran through some code which is also on our screen here. So for this particular code, we know that it's going to display on the first segment here. So based on the combination which we did in class, which I showed you, the combination for the A0 and A1, can now be able to switch between the several segments. And to do that, like if you want a particular port, which is either the A1 or A0, if you want it to come up, or if you want to select it, you use the code or the instruction set bit or set B and that particular port or pin. Then if you don't want that pin to show, or if you want it to be zero, since we are using ones and zeros to demonstrate, if you want it to be zero, you use the instruction clear, CLR, clear instruction. So let's run this code, this one, then we'll see where our LED would display. The 7 segment will display. So if you run this, you can see it's on the first segment, which is the display 3. So let's pause this and reset. Let's make this clear. Then you can run this. So you can see now it's on the second one, which is the display 2. You can pause this, reset, set B, then clear, run this. You see it's display on the third one. Then reset, then this clear for the fourth one. So if you do this, it's going to display on the fourth one. So to select, you use the word instruction set B, and to clear or to make it zero, you use the instruction CLR, which is clear. So well, this particular one, you actually use it in one of your any of the, I think a particular group will pick that one of the groups of the mini project, you actually need this as well. So take note of that. It's for everybody, so take note of that. All right, moving forward, we'll go into what to actually have for today, which is the PSW. Let me do this. Draw. Okay. So PSW, that's what we're doing today. All right. So basically, what does PSW do? What's the function of the PSW? It's the PSW register. It's in our notes, anyways. It simply shows the status of um, every operation or each of the operations that has been carried out in our ECE51, and we know that it has 8 um, bits. Is of 8 bits. You can see that from EdSim here is of 8 bits, and out of these 8 bits, only 6 is being used by the ECE51 microcontroller. So we have the most significant bit is called the. So let me click this so you see. So you can see that you have the CY. The CY is called the carry bit. You have that. The next one is auxiliary carry. You have that. Then this FO. FO is for user bits. Yeah, that one is user defined depending on what the user wants that particular bit to do. Then for this bit is the SR bit, which is the SR1 and SR0. They are more or less like register bank selectors. So when you're dealing with a memory organization, you actually see how the register banks are. Yeah, so they are used these two bits are used to indicate which of the register bank is selected. Then you have the overflow, yeah, and you have this particular one. Though this particular one is a reserve bit, it's just reserved, it's not used. So depending on the operation that is being carried out, if you require more bits, you can actually use this bit to display that. And the least significant bit is called the parity bit. And you know what, I've actually mentioned what they are. So let's move on to do some demonstration of these various PSW and see where they come in. So the first one will demonstrate for the carry bits, sorry, the carry bit CYW, CY, CY. So we'll have so let's pick a number. I'll just pick a number that will be able to help us demonstrate um that. So doing that, we have 1 1 0 0 0 0 0. I have 0 1 0 0 0 0 0. So I think this should be C0H, and this is 40H. Yeah, so now we want to perform the add operation. So let's add this binary number 00 00 00 00 00 00 So 1 plus 1 in binary will be 0, carry 1. 1 plus 1 also in binary will be 0, carry 1. So you're having a carry 1 bit out of the 8 bits. So what that means is that our carry bit here, or CY, would be equal to 1 because we have a carry in our operation. So we can also demonstrate this in our EdSim. So let us write our code for the demonstration for carry flag. Okay, so let's assemble this for error, so no error. And we can, of course, we can do this step by step. So we have moved the C0 to accumulator. Now we need to move the 40 to register R0, which is this. Now we have to add that value and save in accumulator. So we can see, if you observe, the accumulator is now 0 because from the addition here, this we are having a binary number as 0 with 1 as a carry. So if you check your PSW status now, you will see that the CY flag has become 1 to indicate that there is a carry in that operation. And what is saved in the accumulator is 0 because what we are having as a summation here is 0. So that is that indication for um, the carry flag. So next is the auxiliary carry. So let me erase this. Sorry. So delete this. So auxiliary carry. Okay. So let's have now one thing with auxiliary carry, for auxiliary carry to happen, it's when a bit, you're carrying a bit from, or when there's a carry from bit 3 to bit 4. Remember from your PSW, this first one is 0 bit, bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, which is a total of 8. So when there is a carry from bit 3 to bit 4, you have an auxiliary carry status indicator. So let's move on to for that demonstration. we'll have 0 0 0 0 1 0 0 0, have 0 0 0 0 1 0 0 0. So if we add this, this will be 0 0 0 1 1 1 will be 0 carry 1, so 0 carry 1, and this will be 1 0 0 0. So what this means is this bit is our third bit and this is our fourth bit. So from the third bit to the fourth bit, there is a carry of one bit to the third fourth bit. So with that, our auxiliary carry indicator would come up. So we can also demonstrate that and see. And if you convert this to binary, you also see the value in binary. So instead of writing everything, so let's write the binary equivalent of this. This is 0 8 and this is also 0 8. It's still the same thing. So assemble, no error. So let's move step by step. Okay, sorry. Let me just copy this. So set. Okay, let's go. So step, we are moving 80, we are sending it to accumulator. Next step, R0, we are also sending 8 to accumulator. Now we need to add. So on in our addition, we can now see that the carry flag is now indicating as 1 to show that there is a carry from bit 1 to bit 3 to bit 4. Yeah. So that's how to show that. For just take note, for auxiliary carry there needs to be a carry from bit 3 to bit 1. Yeah. So in here you have your AC equal to 1. That is for auxiliary carry. So the next one is what the user defined bit. The user defined bit, like we said, it's based on what you want to set or what you want to use it to do, what you want to use that particular bit to do. So let me erase, close. So for user defined bits, it's for us to demonstrate it is very simple and direct. So you just to say, okay, I want this bit to be set, or I don't want it to be set. If it's set, then if I want it to be set, then or if I want to use it, then I should give it a signal which is 1, and if I don't want to use it, I make it 0. So we can just erase this. It's also a simple code, simple program. So we just go straight to set F0. So if we don't want it to work, or if we don't want to use it, like I said earlier on, if you don't want to use it, you set it at 0 with the CL arrow flag F0. So you can assemble to check no error. So now what is mean the first one? So let us see the step. Let's step the first one. So you can see that the F0, which is it's now 1. So it's now set to 1. If I want to clear it, the next step, so I don't want to use it, I've cleared it. So it's now set to 0. That's just the simple way to demonstrate for the user defined bit. You either set it or you don't set it, or either select it or you don't select it. So that's the next one. The RS1 and RS0, like I said, they are used to for to indicate the register banks. They are for register bank selectors. We can't go into register bank now because it's under the memory organization. But basically, in we have about 4 banks. Bank 0. Sorry, we have bank. Let me say B0 to B3, and it goes in, yeah, from down to up, which is I think ascending order: B0, B1, B2, B3. Yeah, and for us to select each of those banks, we should have a combination, just like we had in our decoder for A0 and A1. So for the register bank selectors, sorry, for to select a particular register bank, we need to use the register bank selectors to do that. And for that selector, the combination, so we have RS1 and RS20. Sorry, so the combination is 0001, 10, and 11. So for this, if we want to select bank 0, our combination will have to be 00 for bank 0. For bank 1, the combination will be 01. For bank 2, the combination will be 10, and for bank 3, the combination will be 11. Yeah, so when you get to when you're dealing with the memory organization, you see those banks. Yeah, so that's for the RS1 and RS2. Now the other indicator here is the overflow. The overflow. So basically, in most cases, overflow tends to happen when maybe there is a division, or um, when you're dealing with a signed bit. I think when your last class signal systems and theory, you actually came across signed bit and unsigned bit, and when you're dealing with the trees, complements, and all. So for a binary number that has 1 as the most significant bit, you realize that it's actually more of like a signed bit. So you literally have a negative 1 represent negative, 0 represent positive. Yeah, so in most cases, if your answer is if you're dealing with a signed, yeah, a signed number operation, or notation, if you're dealing with a signed number notation, sorry, unsigned notation, then this tends to happen, the overflow tends to happen. But if otherwise, then it doesn't happen. So we'll actually show a demonstration of that. Then basically, it turns out to be that a negative sum, if you have a negative sum of a positive of operand, then there will be an overflow. I would actually explain that. So let's just pick an example. So let's pick a binary numbers. Sorry, to select this. Okay, so have 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0. So do an addition. The hexadecimal value for this is 6th, while this is 46h, and the binary number for this is 90, while this is 70. Now if we do our addition, so let's add 0011 01 01 0 0. This will be 1. This will now be 0 carry 1, so this becomes 1. Now since we are having this as our final answer, it means the most significant bit here is 1, which means that the answer would eventually be a negative answer. It will be a negative number anyways. So I think negative is unsigned. Yeah, negative is unsigned, or one of them I think should be. So when you're doing your signed and unsigned numbers, I think one of them is the negative is unsigned. So if we do this, we realize that um, the binary equivalent of this number, or the hexadecimal equivalent of this binary number, should give us A6. Should give us A6H, and this, if we add this together, this should be 166. 166, sorry, that should be 160, not 166. But A6H in binary would give us minus 90. A6, I think that should be 90. 90. So because this is a signed number, because you're having a 1, and one, if 1 is the most significant bit, then it's going to give you a negative. So you'll be having a negative answer. But meanwhile, these are positive binary decimal numbers, and adding positive decimal number, they shouldn't be having a negative answer. So if in such cases like this, if it happens, it simply means that there is an overflow. There is, in a layman term, you can call it, there is an error somewhere. Yeah, there is an error somewhere. So that's how the overflow tends to happen. So we could actually have a demonstration, a code demonstration of that. Let's see how it's going to work. Move a comma hash 60h, move r0 hash 46h, then add a r0. So let us assemble and see. Okay, no error. So let's go step by step. So I'll move this to accumulator. I'll move 46 to R0. So now let us add and see. Okay, so now we are seeing this. We are seeing that our overflow is showing 1. So it means that there is actually an overflow our in the summation. So which simply means that if you're having a negative sum of a positive operand, then there is um, or an overflow will definitely occur. Yeah, so that's um that's how the overflow is. And the last one is, okay, like I said, this other one is the reserve bit. Well, there's no demonstration for that, so it's based on, it's not used, so it depends on whatever, just for in case. Yeah. And the last one, but not the least, is the parity. I mentioned this in the last class. The parity is used for what they call it, to indicate the number of ones in a particular um, number, number of ones in a particular number. So we can do that. So let us do this. So let's indicate, let me comment this and comment this. So we're saying that we should move 60. If you look at 60, it's already here. We already have 60, the binary equivalent of 60. I'll have 2 ones here. And for 46, we are having 3 ones. So let's see, let's run this and see if our parity will be 0 or 1. So we said odd parity give us a 1, while even parity give us 0. So let's run this and see. So we have moved 60 to accumulator. Is that, since our binary number is 2 even, our parity is 0. Pause and reset. I will now comment this and open this, and I'll run and see. Nope. Sorry, no. This should be in accumulator. A. Let's run. Yeah. So it's in the accumulator. We run this. We have 46. We have moved it to accumulator. And we say 46 is what? 3 number of ones. So it means our parity would be 1. Yeah. So if we pause this, reset, and we use this A6, let's see what's going to happen. A6 run. Sorry, since it's starting with a letter, so you should make it. You have to make it 0. So let's run. A6 is even. 1, 2, 3, 4. Even number of ones. So our parity would be 0. Yeah. So that is how the program status words are being indicated in EdSim, and maybe wherever you're dealing with a microcontroller entirely. And so I hope that this will be helpful um, going forward. Yeah, thank you very much and have a good evening. Okay. Right. Where's this one? Why is it not going? All right. Thank you. Have a good evening.